when I first came to Stony Brook as chair of the math department, I determined to learn more about characteristic classes, which are something in mathematics, about in bundles and so on. And I thought a good exercise would be to find a combinatorial formula for what's called the signature of a four-manifold. It's a typical characteristic class. Everyone knows there's a combinatorial formula for the Euler characteristic. It's vertices minus edges plus faces. So I thought maybe there'd be something like that for this invariant of four manifolds. And I struggled and made approximations and so on, but there was one pesky term that I couldn't deal with at all, and then this term seemed interesting in its own right. So M is a closed-oriented three-dimensional manifold. This is its frame bundle, oriented frame bundle with fiber SO3. And so theta ij and omega ij are the connection form and the curvature form. Ij go just from 1 to 3, and theta ij is minus theta ji, and omega ij is omega ji. And this is the standard structural equation. The differential, the exterior differential of theta ij is, well, what it says here, omega ij minus the wedge product of theta ik and theta jk. Now, here's a three-dimensional differential form called Q. I'm calling it Q. And it was this form, sort of, that came up as this pesky term. Anyway, so it's easy to see that this form is closed. D of it is 0. That just follows just from the structural equations that were before. And it's also pretty easy to see that its integral over the fiber, which is a three-dimensional fiber, is 1. Now, the proof of that is since omega is horizontal, if you restrict this thing to the vertical fiber, all you get is this term. And it's normalized. So when you integrate this over that, and it's normalized, it's a multiple of the volume form of SO3. And I wanted it to be 1, so I normalized it by 1 over 8 pi squared, and that makes its integral over the fiber 1. So now, what does it say? Since M is closed, it's a closed three-manifold, it's parallelizable. That means you can find 3 independent tangent vectors at every point smoothly over the manifold, and they can be a frame, an orthonormal basis at every point. That's all oriented three-manifolds have that marvelous property. So now I want to integrate this over a cross-section. I want to integrate Q over a cross-section in this fiber bundle. So a cross-section is mapping the three-manifold up into the bundle, then integrating that over its image, integrating Q. And it says here that if I integrate it over one cross-section and then I integrate it over another cross-section, the difference is going to be an integer. Well, why is that? Well, homologically, one cross-section equals another cross-section. This is homologically up to boundaries and stuff, plus some integral multiple of the fiber, and plus torsion. So when you integrate Q over psi, it's going to be equal to its integral over psi prime, plus an integer, and of course and it kills torsion. So these two things just differ by an integer. So I define this function of M with its Riemannian structure. And it's a value, takes values in R modulo Z, the circle, if you like. So I just integrate this over any cross-section and reduce mod Z. So that's a well-defined function. So here's a theorem. It's a conformal invariant. It seems to depend on the metric, but if you change the metric by a positive function, you'll get the same answer. And theorem 2, a necessary condition that M admit a conformal immersion into R4, one dimension higher, is that this invariant, this measurement, phi of M, is zero. Now, I discovered that while riding on an airplane with Jeff Cheeger. He's in front here. And I said, oh, I did this integral and these things. It turns out to be zero. I was a little disappointed. And Jeff said, what are you talking about? That's a theorem. I said, oh. Oh, you're right. I said, it is a theorem. And so here's an example. Phi of the real, the three-dimensional projective space is a half. So even though you could globally immerse this into R4, and locally it's using its standard metric, and locally it's isometrically invertible because it just looks like a round sphere, but globally it can't be conformally immersed in R4, and I don't think there's any other way to prove that. Well, maybe there's some other way to prove it, but it was a nifty proof. Now, something else. Phi is a map from the space of conformal structures of a three-manifold into R mod Z, into the circle. It turns out its critical points correspond to locally conformally flat structures. So when you differentiate this function, this is in the infinite dimensional manifold of Riemannian structures or conformal structures. It has a critical point only if it's locally conformally flat. Now, it's well known that a locally conformally flat, simply connected three-manifold is diffeomorphic to the sphere. So, a shortcut to proving the Poincare conjecture could be showing, and some bright guy out in the audience might be able to do this, if you can show it has a critical point if the three-manifold, it always has a critical point if the three-manifold is simply connected, then you will have solved the Poincare conjecture. And that's a one-line proof. All you have to do is see that it always has a critical point. And that has evaded my abilities so far.
But now we know it does.
But we know it does. Yeah, we know it does have a critical point. So, well, there you are. There's the challenge. A one-page proof of the Poincare conjecture. Anyway, I did this work that I showed before. I showed it to Chern. Chern said, oh, well, we can do this in all dimensions and so on, and he was very excited. So we worked together and did a lot of math and published that paper, and Chern and I were very happy. And following that, Jeff and I invented differential characters, and we started the field of something called differential cohomology. So it was all fine in math, but it never occurred to me for a minute that this math would apply to physics. I know F equals ma. That's pretty much the limit of my physics knowledge. Well, maybe I know a little more, but not much. And but then the physicists started picking it up, and it was just serendipity that it seems to be used in physics all over the place. So we have 3 physicists here who are going to tell us how it's used all over the place.
So when I was trying to see what are the kind of connections between Chern-Simons theory and string theory, I said, well, a natural thing would be perhaps to look at the archive to see where we can find connections. And so I said, okay, I'll look at full records here for the word Chern-Simons. Now, that means abstract and the title. Well, you might as well, by the way, notice that this archive itself is sponsored by the generous support of Marilyn and Jim's foundation. So that's already one of the one of the minor things they do. But anyhow, so this is so I put Chern-Simons here to see what comes out, and unfortunately it gave me it says too many things came back, so it didn't give me much. It's only 1,000 of them were displayed. So I said maybe I should narrow it down. I said, okay, just the title then this time. How about just the title having Chern-Simons in it? And not much better. We still got over 1,000, so we couldn't get enough information about how many of them there are. So I went to the Inspire to see whether I can do better. So this was that find Chern-Simon means it finds again abstract and the title. And then you see it's 8,000. Abstract and title, still too many to display. I said, okay, how about just the title? And there are about 3,000. Again, too much to display. So I had to narrow it down to something which is manageable to display something. So I said, okay, how about Chern-Simons and myself? So Chern-Simons and author papers that I have written. Okay, that should be just a few, right? Well, 36 papers I've written has abstract or title Chern-Simons. Now you might say, okay, it's all about one particular area of string theory perhaps, but not really. So I'll display it, and you just look at some of the titles and see how these titles look like Chern-Simons. I just go slowly so you can just briefly scan some of the titles. So as you can see, it's a very diverse range of applications, and it's just one person's encounter with this subject, with this aspect Chern-Simons theory. So it goes on and on. So then I asked to see again something more definitive. I asked Paul Ginspark, who's the founder and the manager of the archive, how many papers use the Chern-Simons term somewhere in the paper? Okay, this will give a better flavor about the diversity of it. And he told me on the average 4 papers every day have this term in it. Okay, so this already is the tremendous impact this subject has had in physics. That's, I think, clear. So what is Chern-Simons? Well, we just heard about Jim the beginnings of the subject, so I will just tell you briefly about some aspects of what's the definition of Chern-Simons action. So we start with a 3-manifold, and we take a gauge connection, a gauge field, which is a connection on the M, with some structure group G. We consider an action which is the integral of this form. You take ADA and 2/3 AQ with some factors times an integer K. You integrate over the manifold M, and here K is an integer, and trace denotes some G invariant form here. And it turns out that, similar to what we just heard from Jim, if you do this evaluation, this is well-defined and invariant by gauge transformations, except we can change by an integer multiples of 2 pi k. And the integer depends, when you do a gauge transformation, what is the map from the manifold to the group. So depending on what gauge transformation you do, depending on the class of this map, you pick up an integer times 2 pi k. So this term, Chern-Simons term, is denoted in this form, typically in the physics literature. And it has the property that if you take d of it, it gives you the trace of f wedge f. And the integral of this trace of f wedge f is rigid. It's 8 pi squared times an integer. And this integer is determined by the topological type of the bundle. So in some sense, it's very rigid. It's the second Chern class. It's a very rigid object. So f wedge f is nice and well-defined, an integer, but it's a bit too rigid in the sense that in physics we typically want things which actually vary with things. So typically, even though this is nice, the Chern-Simons term is not an integer. It's defined up to additions of integer, but it's not itself integer and can vary. So it's more like physics. It varies. It doesn't have that rigidity. And so the Chern-Simon term carries some of the leftover information that's kind of less rigid than this Chern class. That's why I think at least one way to think of why it's showing up in physics so much. And it also does not depend on the details of the metric on the manifold. So it's topological in a sense. It's not completely determined by topological aspect of the bundle, but it is topological in the sense of the Riemannian geometry of the manifold does not play any role. And that those aspects give it, I think, some of the power we have seen in the context of physics. So given this, I want to now say how it began to be used very effectively in the context of physics. Starts with the work that Witten did in defining the Chern-Simons theory, where you take the same action I talked about, you exponentiate it and multiply by an I, so that's now well defined, because if it shifts by an integer multiple of 2 pi, it doesn't matter, so that's a well-defined gauge invariant object, and roughly you want to integrate over the space of all gauge fields. And so physicists have dealt with what this means, the integration over the space of gauge fields or gauge connections. And this is called the partition function Z of Chern-Simons theory, which depends on the manifold, the group that you choose, and also the level, that K, which was the coefficient in front of the action that we have. The equation of motion of the action, if you vary this with respect to A, you find that gives you the F is 0. So this is flat. In the classical solutions to Chern-Simons action are flat connections. And this fact can be used to define knot and link invariance. That's the basic input. So if you define the holonomy around some loop given by a connection, if you move the knot around, since it's flat, this object can only change in its own class. The character of it doesn't change. And so therefore, you can define some averaging. When we were integrating over the connections, you can insert this in that integration and get an invariant, which when you choose the holonomy around some particular, let's say, knot, and evaluate the character in some particular representation, which is what we call trace in representation R of this, and this object will give you some invariant for that knot, which does not depend on the metric. There's a little detail that I'm hiding, but it's roughly this simple picture. And you can do that also for links. So you can take a bunch of knots, and they might be interlinked and so on. And so this kind of captures some aspects of the links or knots, which is very nice. And it is just simply follows from the idea that there is this topological action with these nice properties. So now applications to string theory is what my topic is. So this was basically what Chern-Simons theory itself was. So now we want to talk about how do we apply it to string theory. Well, there are far too many, as I hope I try to indicate by that search. For example, I'll just give you a few of them. It's a model for string field theory for open strings. Chern-Simons term plays a crucial role in anomaly cancellations in string theory. That's one of the reasons string theory exists, is the fact that somehow magically anomalies cancel. Chern-Simons term plays a key role in that. Holomorphic versions of Chern-Simons action lead to potentials that we deal with in physics, actually in model building physics. When you want to apply string theory to our world in 4 dimensions, you end up studying holomorphic Chern-Simons on a 3-complex manifold. Again, important for us. Importance in dynamics of branes, and so on and so forth. So, in fact, when I was preparing this talk, I mentioned it to Ed Witten. I'm planning to give a talk about this subject on string theory, and he says, well, he can prove a no-go theorem that this cannot be covered, this topic, in the course of half hour. So I would not be violating this theorem that Ed proved. So I'm just going to stick to my little corner that I have studied on this subject, the application that I have encountered of Chern-Simons theory and string theory. It happens that these areas that I've worked with actually connects to some other basic important aspects of string theory, which will give you a way to actually connect up to some other topics which are crucial and other aspects of string theory as well. So I will stick to those applications. So the application starts with with basically seemingly completely unrelated topic. Namely, you study, as Witten introduced, what's called topological string theory, which means that usually in string theory, we look at maps from Riemann surfaces to manifolds. So like you take this donut-shaped object with these handles and you try to put it in the manifold. But topological string theory says don't study all possible such maps, but somehow restrict it to the ones which are nice. And in this case, nice means the following. If your manifold M is scalar or just symplectic in some suitable form, you can actually look at the equations which are more special, and that map could be a holomorphic map. So these kind of map have nice properties, and it kind of embeds the surface in a minimal volume, minimal area kind of situation in the surface. So it's a very nice kind of map. And mathematicians were interested in this kind of question called enumerative geometry. They wanted to know how many of these nice holomorphic things can sit in different manifolds. It is a very difficult topic, and people don't know in general how to count these. So it was, even before string theorists got interested in this topic, it was studied by mathematicians to understand enumerative geometry questions involving different manifolds and how these kind of things fit in them. There's also what's called open topological string, which you look at, again, holomorphic maps, but now instead of a Riemann surface being a closed Riemann surface, you have some holes in it, you have boundaries in it. And so what you do is that you take the manifold and you consider some Lagrangian submanifold. This is a symplectic manifold, so you can consider Lagrangian submanifold, and you restrict the boundaries to land nicely on these boundaries. So this is called the open topological string. And these Lagrangians that you put on the manifold, so if this is, let's say, 6-dimensional manifold, you put a 3-dimensional Lagrangian submanifold. These objects, these subspaces that you pick, for physicists, they are objects. They're physical objects, and they're called D-branes. So we call these D-branes. So what that means is that the Riemann surface can end on D-branes. So that was one seemingly unrelated topic to Chern-Simons theory. And yet, this is another yet seemingly unrelated topic to Chern-Simons theory. So this is some basic facts about perturbation theory. So what I'm going to say here is well known to physicists, but I'm going to say just in case for people who are not physicists in the audience. So let me just briefly review this, some basic facts about perturbation theory. Suppose you're interested in carrying out an integral of something looking like Gaussian, e to the minus x squared over 2, plus some other terms, cubic, quartic, and so forth. And suppose these additional terms that you're adding are not that big. Alpha and beta are not that big. They're small, so you can almost assume it's like Gaussian with some small corrections. You want to fix the corrections, so we do perturbation theory. And it's well known how to do it. Well, you can bring it down and just expand and do it, because we know how to compute these integrals one by one. But it turns out that, as Feynman and others noticed a long time ago, this has a nice diagrammatic form. Trying to do these integrals leads to a nice diagrammatic form, and the diagrammatic form is roughly as follows. You consider all kinds of graphs which have cubic and quartic vertices, like alpha and beta points here, related to the fact that there's a cubic and a quartic power here. And you consider all such graphs with certain combinatorics factors, namely, for each graph, you put a factor of alpha and beta depending whether you have a cubic or a quartic vertex, and some combinatorics factor having to do with the symmetry of your diagrams. You sum all the connected graphs, exponentiate it, and this gives you a perturbation series for Z. So this is a graphical representation of this in the perturbation theory. OK, that sounds like a random fact. Now, if you generalize this instead of from real variables to matrices, so instead of x being a real variable, replace it by a Hermitian matrix. So it's an n by n Hermitian matrix, and you start doing the same thing. Well, it turns out you basically get the same rules as you had before with the following change. The x for us, the x squared term for us, corresponds to what we call the edges or propagators, these lines. And now the fact that this corresponds to an n by n matrix means that we have a double edge. The edge is doubled. And each edge carries a label of n. Namely, you can think about this Hermitian matrix as a tensor in the tensor product of fundamental times the anti-fundamental. And these edges carry those indices. So you get exactly the same pictures as I drew before, except now you have to pay attention to the fact that edges are now doubled, and therefore you can get boundaries like this. And for each boundary that you get a factor of n, I guess I missed a factor of 1 here, 4, 5 here. So you just count how many boundaries you have. In this picture, you have 5 boundaries. So depending on how many boundaries you have, you put a factor of n in that, n to that power. Otherwise, it's basically what we had before. Now, this is, and also you can have diagrams which are not planar. You can see, for example, you can have a picture like this one goes over, passes that one. So you get some geometry out of just perturbation theory. And this basically looks like a Riemann surface where these boundaries are the boundaries of the Riemann surface. Namely, you can think about these interior regions as a Riemann surface and these boundaries as the boundaries of that Riemann surface. So simply out of perturbation theory of n by n objects, Hermitian objects, you're getting something which looks like summing over Riemann surfaces. This was actually noted already back in the 1970s by 't Hooft, that perturbation involving n by n objects somehow mimics something which looks like diagrams of strings. And in fact, this is true for not just Hermitian matrices, it's true for anything which involves Hermitian, like Hermitian connection, like the gauge fields. If you're dealing, for example, with a gauge field un, the gauge connection is an n by n objects, and again it assembles itself into these diagrams. So 't Hooft asked, for these un gauge theories which involve n by n, is there any sense in which this can somehow get rid of the holes? So this was his question. Can you somehow, these diagrams which are these boundaries, can you somehow get rid of them in some way? Now this might sound like a random question from a math viewpoint. Why would you want to get rid of it? It's already there. Well, for the physics, the motivation was that for him, this was the quark-anti-quark pairs. And he was thinking about strong dynamics in these theories, and they bind each other. And so somehow he was thinking that in the strong coupling regime, somehow these holes close up, and you get this closed Riemann surface with no boundaries. So he was asking this question, can somehow be related, getting rid of this picture, but he couldn't really quite succeed until more modern days, where the following pictures helped in finishing that story. So Polchinski noticed that you can actually realize 't Hooft's idea that UN gauge theories have something to do as a part of string theory. D-branes are these objects, and they cut open the worksheet, and that gives you the diagrams of the type that 't Hooft was connecting to gauge theory. And in the context of Chern-Simons theory, independently Witten in the 90s found that you can actually realize Chern-Simons theory in this way. Namely, you can think about Chern-Simons theory as what you get in open topological strings. When you take the manifold, if you're interested in Chern-Simons theory on M3, you consider the manifold cotangent of M3. You put n d-branes, n Lagrangian branes around M3, and you do the perturbation theory. And the theory that you get is the same perturbation expansion as Chern-Simons theory. So Chern-Simons theory is a string theory. And so then 't Hooft actually, so the question is, how do you realize 't Hooft's idea that somehow these boundaries disappear? And this is, again, a very big topic in string theory, which began with the work Maldacena did, which showed that a particular gauge theory, in this case n equal to 4 supersymmetric Yang-Mills theory, which has also a 't Hooft type expansion for large n, is equivalent to closed string theory. So in other words, n equals to 4 supersymmetric Yang-Mills, which is these Riemann surfaces with boundaries, in the large n limit, has a limit which has no boundaries. No boundaries means, in physics language, there's no gauge field left over. At least there's no basic n degrees of freedom left over. And that means it's just a theory of gravity. So it relates a gauge theory to a gravitational theory. And that is one of the amazingly important topics in string theory called holography. Connects a gauge theory, in this case a conformal field theory, to gravity, in this case in the context of ADS. But even though there's a huge amount of checks, so we don't doubt this is true, to actually check that this is true to all orders in expansion has not been done. We are nevertheless confident it's true because of the various checks we have done. Now you can ask the same question for Chern-Simons theory at large n. So take Chern-Simons theory for gauge group UN on some 3 manifold, and you say, I'm going to be interested in UN gauge theory when n is large. What happens there? And the answer to that was found in the context of Chern-Simons theory for the 3-sphere. If you take it to be a 3-sphere, we found that if you take the geometry of n d-branes, here I'm drawing the geometry of cotangent of S3. Cotangent of S3 has a boundary, which is S3 times S2, the cone over it, except that the cone, in the apex of the cone, instead of having a point, you have S3. So you wrap n d branes around the S3. This is just the geometry of cotangent of S3. So what happens if you have a large number of branes? Somehow the dynamics of the branes pushes this S3 to become zero size. So you go through a singular geometry. S3 shrinks to nothing. And then you go undergo a geometric transition where this S2, which is at the boundary on the other side, now becomes a finite size. So the branes disappear because they were wrapping their Lagrangian objects. Now you get rid of them, and you replace it by a two-sphere. So we can draw the same thing if you go by toric description of this geometry. You can look at the toric picture, which is denoted here. You have these green lines here, which depicts the branes, the location of the branes, suspended between these 2 points. You can think about this as a Heat-Guard decomposition of a three-sphere. So when you have these circle actions, this is where the one circle degenerates, and this is when the other one degenerates. And you can think about this interval times the torus as the Heat-Guard decomposition. So the Lagrangian transition simply says that this goes to zero size, the lines cross each other, and then you get a new line like this, which is the geometric transition. So the geometric transition will be related to the simple picture. And then this actually can be proven. Namely, you can compute both sides. You can compute the Chern-Simons theory on this side, and you can compute this side, which has nothing to do directly with Chern-Simons theory. It's just topological string holomorphic maps into this geometry. You can compute them to all orders in genus and check that they actually agree. So this one is actually the first kind of check where you can actually prove to all orders that holography works. And that's what we did. But you can do more. Namely, you can actually use this picture, the local geometry of these branes, to construct, to kind of engineer more interesting geometries. For example, each little piece here depicts the picture I had before, which gives you a P1. But you can have P1s collecting to each other and giving you non-trivial geometries of this type, torically, whose answer for the holomorphic curves was not known before. So if you're interested in enumerative geometry for these kind of manifold, which is basically what they call is toric threefolds, toric Calabi threefolds, the answer for them can be obtained by first realizing it in this Chern-Simons form. And the basic link is that there are these tubes which end on these different Lagrangian branes. And if you want to compute it, what you need to do is that you notice that at each, when these tubes end, you end up getting the hopped link. So you compute the Chern-Simons invariant for hopped link for each of these four corners. You sum over all the representations pairwise, which is linked between them pairwise, with some exponential factors having to do with the size of the representation. Sum over all of them, and magically you get the answer for this one, which was unknown. And after this was done using Chern-Simons theory, this has actually been proven rigorously mathematically as well, that this actually agrees with the answer that if you compute this topological string or what's called Gromov-Witten invariance, you get the same answer.
This is this Bosch triptych, which I love about different worlds, Earth, heaven, and the other one. And in some sense, from a computational point of view, we're on the verge of emerging into a new computational world with quantum computation. And I think once we're there, the glimpse we get from its computational power into the quantum world will really be similar to what we saw with the microscope and the telescope. We'll be able to look at questions that where there's simply an exponential barrier that we can't get through now. But the classical world is, rather weak and disappointing thing. I've come to the conclusion as I've aged, and it's what it is, and we all live in it. But it's really just one of these shadows on Plato's cave, and that the quantum world is really where it's at. The universe processes information quantum mechanically, and perhaps soon we also will be able to process information quantum mechanically. Now, there's some people who say we already do. This is a little known subject that I've only very recently become exposed to, and it's called quantum cognition. And Matthew Fisher is one of the participants in this field. I know him from UC Santa Barbara, and this is a quote from him: "Are we quantum computers or merely clever robots?" The field actually breaks into two flavors, actually much like string theory, A and B. They're the people who believe or hope to believe that there is literally quantum processing in the brain, probably from spin of nuclei, since only nuclear spins are sufficiently isolated from their chemical environment to retain quantum information over reasonable timescales. And Matthew is developing a research program, interestingly funded by the Chern-Simons Foundation, to explore whether phosphorus nuclei can process information in the brain. Plan B is, well, it's sort of agnostic. Maybe you don't believe the brain is really quantum mechanical, but empirical observation is that we're so screwed up that unless we take an effective quantum model, we'll never get anywhere in figuring out what we're thinking. So let me just give you an exhibit for A and an exhibit for B. So this is a page from one of Matthew's recent PowerPoints explaining maybe a key moment in his story about how possibly quantum mechanics might be involved in neural processes. So what he did is he looked at the chemical elements which are common in the body for a spin-a-half nucleus, because only spin-a-half nuclei have sufficiently small or vanishing electric higher dipole moments that they will not be scrambled by various electric fields which they would encounter in the body. So the only element that fit the bill was phosphorus. It's very unfortunate that phosphorus only has one stable isotope, phosphorus 31, because if it had another stable isotope, you could easily breed rats with this other kind of phosphorus and see that they couldn't get through a maze, and that would. But you don't have this simple test by which to destroy the theory. Now, in this picture, the phosphorus still has to be very well protected. It has to be kind of caged around by spin zero nuclei. And the most oxygen and calcium are both spin zero. And there are these complexes important in bone formation called Posner molecules, which are made of 4 phosphate groups and 9 calciums. And there's so altogether these 6 phosphorus nuclei have sort of a 64-dimensional spin space, and it's acted on by 3-dimensional symmetry, and it breaks into 20, 20, and 24. And Matthew has a story where this decomposition, there's a pseudospin, and in the binding of 2 of these Posner molecules, as in bone formation, a projection is made onto a joint spin state. And the idea is that because this was developed in our bones, biology is conservative. If something's developed somewhere, it's used somewhere else, that this is the way, a link between spins and chemistry in the brain. So I think it's a very speculative theory, and not one I would jump in to endorse, but I think there's a good scientific program to research it, and it's very imaginative. Then the B school, this goes back, I think almost to the birth of quantum mechanics. I mean, there were always philosophers who wanted to jump in and say, Carl Jung and Pauli had exchanged letters about collective consciousness and quantum mechanics. And psychologists have long studied various quirks of thought, and some of these have been modeled quantum mechanically with various degrees of success. Actually, this Ellsberg I mentioned is the famous Daniel Ellsberg, who got the Pentagon Papers. So I won't tell you this paradox in detail, but you can look it up on Wikipedia. It's something about a urn with 90 balls in it of 3 different colors, and you reach in and you grab a ball and you get a certain $100, you know, depending on some bet you've made about what kind of ball you'll pull out. Now, it turns out that if you give people 2 choices of bets, like 90% of them will pick bet 1 over bet 2. But then if you add the same constant payoff to bet 1 and 2 to make it bet 1 prime and 2 prime, then 90% of people will prefer bet 2 prime. So it's why? So there are various mysteries, and if you think about, you know, psychology, you can't really like measure all the observables. You know, if you're going to question someone, you have to decide which question to ask. You can't ask. Sometimes one question will create a mood that you can't ask the second question. I'll let you all think of your own examples. And this is very much like quantum mechanics, where you have to pick your variables. You can't measure everything. So, you know, this is sort of people who think, well, maybe there's nothing quantum mechanical at root, but maybe the effective model is quantum mechanical. So our thinking is very puzzling, sometimes even to our pets. Now, what I've been trying to do in my professional life for the last decade or more is build a quantum computer. But I've sort of turned that over to people who know more. And I'm thinking now about what we'll do with it when we have it. I think that's my greatest concern, is what problems will it solve. And scientific problems like fermionic Hubbard model, that's a great application. It'll certainly work gangbusters on that. Quantum chemistry has been explored. You know, it won't work right out of the box, and I think basically the reason is that classical quantum chemistry is already pretty darn good. We've been working on it for 100 years, and we have great numerical methods, and if you want to get activation energies to a millihartree, you're going to need a quantum computer that can do like 10 to the 14, 10 to the 15 operations. So eventually, quantum chemistry will be a great problem, but not for the first generation. Materials like science, like high-TC superconductors, for example, will be even harder. Actually, interestingly, this is probably symbiotic with classical work going on at the Flatiron Institute, Andy Millis's numerical physics group there. Factoring, a famous application, I just say stay clear of that. That will just get one into trouble. Quantum machine learning actually looks extremely attractive. Now, I have to admit the main reason it looks attractive is we don't know how even classical machine learning works, so we can speculate quite a bit about how much better it'll work quantumly. But the main lesson I would take from the quantum chemistry example, which my colleagues at Microsoft worked quite hard on and made progress on, is that we need something without a good classical approximation if we want an early application of a small quantum computer. And I think human decision-making is very attractive this way. It's a high-value target, and the present methods are quite primitive. And in thinking about this, there's a game that I'd like to try to make a quantum computer learn to play against a person. This is the simplest possible game. It's for people who don't have the mental bandwidth to play rock, paper, scissors. It's the mod 2 version of rock, paper, scissors. I throw out a binary bit, and you throw out a binary bit, and I win if they agree, and you win if they disagree. And the von Neumann equilibrium strategy for this game is just to throw out a random string, and it can't be beaten. But it also can't win in the long run either against any other strategy. So if you're actually playing against a person and want to win, you have to deviate from the conservative strategy. So I think this is an interesting problem. Actually, Scott Aronson has on the web a game where you can compete against a classical robot, and the robot will get into your head and beat you pretty quick. But if quantum circuits are good at this game, perhaps compared to classical circuits, for instance, I think it's not such a far leap to say that human decision-making in general might be a topic where quantum models are useful. I mean, if you think about how people will in a competitive way select zeros and ones to try to stay ahead of you, it's not so different from how they would play poker or perhaps how they would buy or sell shares of stock. So that's the thought. It's the minimal model for testing how people think, how they generate zeros and ones in a competitive manner. So where are we? We haven't actually put this game out, but a colleague of mine, Dave Wecker at Microsoft, has trained a quantum circuit to land the lunar lander. And here it is. So now what goes on in this little demonstration? There's that's the quantum circuit he uses, or some variation of it. And this is a two-dimensional rigid body problem. So its phase space is 8-dimensional. It's like describing 2 points in the plane is enough. So there are 2 position points, that's 4, and then 2 momentum, so that's 8. And those are the numbers theta y0 through theta y7. So about 100 times during this landing, or 50 times or something, the position and momentum of the lander are sensed. And then the other thetas to the right are the things that the machine has to learn. And then it crunches along and does these unitaries, composes them, and eventually measures some qubit. And then according to the output of that qubit, fires little jets on the side of the lander. And now this circuit does not know as much physics as Jim. It does not know F equals ma. It's learning the only way it learns is it learns it's crashed or not crashed. And actually it learns like how hard it hit if it hit. It's some kind of qualitative thing about it. And then by doing tens of thousands of these runs, it just learns which unitaries to stick in to react to which kind of events and get itself down safely. So it's one of these ridiculous machine learning things where there are no concepts that we understand. It's just doing some unitary and some thousands dimensional Hilbert space, and it's rolling things around and it learns how to land on the moon. So I want to do something similar to see if you can learn to beat you at rock, scissors, paper. Now for long computations, I think it's clear that topology will be needed. I think this is what we're learning at Microsoft by watching our competitors. I think you can go very fast to 50 qubits and do 50 gates on them or something. But if you want to compute for a serious amount of time, you'll need topology to protect information. And this is where the Chern-Simons Lagrangian comes in. It's sort of the icon for topology in physics. And just to say, very briefly, why is it so darn important? Momentum occurs to first order in the Lagrangian. In space terms, you see one derivative of A instead of 2 derivatives as you'd see in a Maxwell term. So that means when K is really small, like epsilon, then this term is of size epsilon, whereas a Maxwell term would be of size epsilon squared. So if you think about renormalization, if you're looking at cryogenic systems, it's very natural. If there's something Chern-Simons going on there, that'll be the dominant effect at low temperature. Second point is you see no metric. So it is really a topological term. And I'd say historically, it's not the only gateway of topology into physics, but it's overwhelmingly the most important empirically. And the gateway made it into my world. As a topologist, I also learned no physics in those days. They were separate subjects. It made it through this work of Witten, which Kiram already mentioned, where he explained Witten explained the Jones polynomial as the observables, the evaluations of Jones polynomials with the observables of a SU2 Chern-Simons theory at different levels. And it made it over the next 8 or 10 years farther into condensed matter physics in terms of explaining the quantum Hall effect through work of Reed and Green, and then very concretely this Fradkin, Nyack, Tislev, Wilczek paper, where a very particular quantum Hall state observed at filling fraction 5/2 was explanation for its statistics was proposed in terms of Chern-Simons theory. And in fact, it was this paper that made me hire Chetan at Microsoft and really started our program to try to build a quantum computer. We literally wanted to turn this paper into a computer. Well, it turned out it didn't work too well, and people were mumbling things at the time like, well, that's really not a well-controlled solid-state system. What about yield of devices and things like that? And we just ignored all that. But eventually, we kind of worked our way into a system that is sort of a dimensional reduction of Chern-Simons theory. It's not literally Chern-Simons theory, but what we found is a simpler one-dimensional model that has fermionic boundary excitations that obey the same braiding statistics as the fermions in SU2 level 2 Chern-Simons theory. And this is what it is. It's the Kitaev chain, and now it's written down in kind of condensed matter notation, creation and annihilation operators. The first term is a potential term, and this is a hopping or kinetic term, and those are superconducting terms. And what it can be visualized is that if you take the annihilation operator and break it into real and imaginary parts, these are so-called Majorana operators, which are Clifford algebra generators. And when you tune the hopping and the superconductivity, you find that the bilinears in the Majoranas, sort of, which are indicated by the bonds in this diagram, go between rather than within the electrons, which are the ovals. So you could, and leave free zero modes, Majoranas that are outside the Hamiltonian at the ends. And this is where the information is stored. And like my icon of this, it's like a chain of paper dolls, and the free hands are, each electron is two hands, a real and imaginary Majorana. And the free hands are the degrees of freedom that are used in the computation. And then it took several years to turn this into a condensed matter system using a high spin orbit coupling nanowire, indium arsenide, and an aluminum superconductor. This is the same Hamiltonian, essentially, but written down in different notation, or more precisely, this Hamiltonian has the previous Hamiltonian as its tight binding model. The key point about the construction of this material and the Hamiltonian is that the two branches of the electron's momentum coming from spin up and spin down are resolved using superconductivity and spin orbit to a single branch. So basically, you're synthesizing the spinless fermion of the idealized Majorana chain in an actual condensed matter system. I'll just skip this slide, which is sort of redundant. This was then carried out physically by amazing materials growth, where the semiconductor is on this side and the superconductor on this side, and you see that that cartoon shell is actually made with exact lattice registry, which allows near the interface the electron to pick up properties both from the semiconductor and the superconductor and create, essentially realize that mathematical Hamiltonian. And then, so the theory, the growth, and then the experiment. And again, I'll be very brief, but this is an experiment showing that as you change the magnetic field as it goes to 100 millitesla, a tenth of a Tesla, these are Coulomb blockade peaks, and the brightness is conduction hopping through a small superconducting island, and as you change the potential on the island. And what you see is when there's low or no magnetic field, you have to change the potential for a Cooper pair to hop. So you see double hop, double hop, double hop. These are these big jumps. And then at the transition where the open hands of the doll chain open up, it allows one electron to jump into those hands instead of a Cooper pair. You see that you have periods at twice the frequency or half the charge. And then a detailed analysis of the little wiggles of the conduction are deviations from the model of these states, these end states, from being idealized zero modes, which is the case at infinite separation. But they become better and better zero modes the farther they're separated, which is physically how long the semiconductor wire is. And the fact that the wiggles go down in this exponential way allows us to extract the correlation length of the material. So sort of from Chern-Simons theory, to a solid state model, to a material, to experimental data, has been the progress of the last, 6 or 7 years. And now I wish we had this. This is made in Photoshop rather than in our lab, but in the next several weeks we should have something like this. And what this is well, this is sort of our roadmap. We've planned out something that's sort of a periodic design where qubits, these are the Majorana modes, and these are superconducting islands, can be arranged and gated and read out by semiconductor dots. The strategy is dots are coupled to a pair of Majoranas, and the commutation relations on the Majoranas throw some interesting signs into the energy of the dot when calculated in perturbation theory. So when the dot is coupled to a pair of Majoranas, you can actually measure an eigenvalue of I gamma 1, gamma 2, which is a qubit. So I'll skip through the details of the measurement. The one last slide I wanted to show was braiding. I mentioned that the braiding statistics in this one-dimensional system were the same as in Chern-Simons theory at SU2 level 2. But you might be confused because the Chern-Simons theory is a two-dimensional theory, and the theory we're actually building is a one-dimensional theory. So how can you even talk about braiding in 1D? But braiding can be simulated by measurement. And this is a little video where if you want to braid A and these two A's, you bring in these two blue particles out of the vacuum and you measure them. The ellipses are the measurements, and these two pictures correspond. That is, now you measure the first and the third over. That corresponds to a world line where you go through the vacuum between the first and the third particle. So a sequence of measurements turns into ultimately a braiding. So it's possible to simulate the braid rules in the 1D system, which seems technologically better than trying to build the 2D system. So that's really the end of the talk. Happy birthday, Jim. Just a quick review of mankind's entire history is we invented fire, numbers, machines, better numbers, computers, well, biology, and then finally a third kind of number, the kind of number you keep in a quantum computer. It's a new way of representing number. You can represent bigger numbers because you can have access to enormous state space.
Actually, I had two questions. One technical one is I thought Majorana modes were really not quite enough to make a general quantum computer.
That's right.
Okay.
Yeah. So you only get the Clifford operations, and you have to augment that with basically any additional gate. And there's a procedure called distillation for improving using only Clifford gates. So general error correction is a very difficult problem because the gates that you use to error correct themselves contain error. But there's a very special sector within error correction called distillation, where you use only presumably exact Clifford operations to improve the fidelity of some other ad hoc operation. So the quantum computer I was describing would need to use distillation. If we get control of Fibonacci anions, we won't need that.
Yeah. Okay. A second question is, if you could elaborate slightly on what you mean by measurement. Naively, measurement, depending on how you interpret it, either means that your system becomes entangled with something else, which is probably a nuisance, or possibly you project onto a chosen state, but then after n steps, the probability that your computation continues is 2 to the minus n.
Were you referring to the last sequence of slides?
When you discussed measurement as an alternative to braiding.
Yes. Yeah, right.
So it seems that either the probability of success is negligible for
that's a very good point. Backwards. Sorry, that's a lot of clicks. Yeah, so I hid a very good question. If you read up on the text, I said forced measurement. And that's a shorthand for a whole protocol which gives you a way out if you get the unpreferred outcome. So when you measure two of these Majorana particles, what you're actually measuring is the joint fermion parity, and you can get a 0 or 1. And what I displayed in this view, in this little movie, is the optimistic scenario that you always measure 0. Now, if you measured 1, what it would mean at this, like when 1 and 3 are jointly measured, there'd be a psi line connecting them here. So you'd have a different, but if you, and what forced measurement is, it's just a little loop where if you get the wrong outcome, you go back and measure a different pair and then go back and remeasure. And that re-scrambles the situation. So that you, again, at each point have a 50-50 chance on the outcome. So it's statistical. There's a small tail that you'll never succeed, but it decays exponentially. So the expected time to success is probably something like 3 measurements for every one I've shown.
I have known Simons, as in Chern-Simons, for almost my entire career. And actually, I can still remember when I first learned about it. It was about 30 years ago. I was just finishing up my PhD, which is about something else. And one of the first trips that I went on, I met a theoretical physicist named Steve Girvin, so maybe some of the physicists in the audience know Steve. And Steve explained to me about the fractional quantum Hall effect in a way that I could understand for the first time. Okay, and in particular, Steve explained to me that you can understand the fractional quantum Hall effect by thinking about a Chern-Simons term. And so I remember learning that and thinking, that is the coolest thing I've ever learned. And I went home and I was completely energized and basically made the decision to change fields. And and of course, I'm not that wise. I had no reason to know it at the time, but that was a really good decision. And over the last 30 years, I've been able to watch as an incredibly beautiful field has unfolded in front of me. And I've had the very good fortune to be able to play my own little small role in some of those developments. And so that's what I want to describe to you today. I want to describe to you Chern-Simons in condensed matter physics, and there's sort of 2 different ways in which it shows up, which they're related to each other, but it's really different. And the first one that I want to describe to you is in the context of the band theory of solids. Now, band theory was one of the biggest triumphs of quantum mechanics in the 20th century. It's probably the most consequential theory that we have in physics. It's the theory that underlies our understanding of all kinds of electronic materials, okay? Semiconductors, okay? So the technology that underlies the information world that we live in today ultimately derives from our understanding of the band theory of solids. Now, so band theory, of course, was developed more than 80 years ago, but it was a relatively recent development that it became clear that band structures can have topological content, okay? And so the understanding of the topological structures in band theory were brought out by some beautiful physics, namely the quantum Hall effect, topological insulators, topological crystalline insulators, topological superconductors. So I want to describe some of those things. And so one thing about band theory is that it's actually kind of simple. It's basically something that you can understand in terms of the quantum mechanics of a single particle. Okay, and so that makes it manageable. And that makes it something where you can get very, very detailed, specific information about specific real materials. And this is the band structure of silicon. The fact that we can do so much with it is because we have control over the very specific materials. Now, there's another context in which Chern-Simons enters condensed matter physics, and this is it's a somewhat deeper sort of idea, which is in the context of what I'll call topological field theory. And what topological field theory is, rather than being a theory of specific materials, it's a theory of phases of matter. Okay, and what a effective field theory is able to do, it's able to characterize the essential emergent properties in strongly interacting particle systems that are composed of many, many, many particles. This is a much more difficult problem, but effective field theory allows us to get a handle on understanding the emergent behavior. And in topological phases of matter, they can have remarkable kinds of emergent behavior, okay? And particularly the fractional quantum Hall effect, which leads to, it's made out of ordinary particles, electrons and protons, but it has emergent properties that have fractional charge, fractional statistics, and can also, ultimately be used for developing technologies of quantum information. Okay, so I want to describe this, and I'm going to start by describing the sort of most basic, or not the most basic, the mother of all topological phases of matter, which is the quantum Hall effect. So this is the topological phase which we understood first, and it's the one that we understand the best. And so let me tell you what the quantum Hall effect is. So the quantum Hall effect occurs when you confine electrons to a two-dimensional plane. Okay? And this is something you can do on the interface between two different pieces of semiconductor. On the two-dimensional interface, you can arrange it so the only way that electrons can be is in the plane. And so back in the 1970s and 80s, it was, understanding the electric properties of these interfaces was a key technological problem, because people were developing the kind of semiconductor structures that go into that are now in your cell phone. Okay, and developing the technology of those semiconductor devices, that motivated people to very carefully measure the electrical properties of these two-dimensional electron systems. Okay, and von Klitzing made an amazing discovery. Okay, by measuring, he passed an electric current down this wire and measured the voltage perpendicular, and put it in a magnetic field. And as a function of the magnetic field, what he observed is that the Hall resistance basically undergoes these sort of step-like behaviors. Okay, and upon looking closer at these steps, it was realized that that the value of the resistance in these steps is incredibly accurately quantized in units of this fundamental constant. This is Planck's constant and the electric charge. And so these fundamental constants define a unit for the resistance. And the value that's measured is an integer that you can measure to 1 part in a billion. Okay, it's incredibly accurately quantized. Okay, so actually, this type of measurement now forms the standard of electrical resistance. Okay, so if you go to the standard of what the ohm is, it's based on this kind of experiment. Okay, and or another way you can say it is this gives us a very accurate way of measuring this combination of fundamental constants. Now, there's something remarkable about this. Okay, because the device that von Klitzing measured, it wasn't a perfect device. So this is a picture. This actually isn't von Klitzing's device, but it's one like it. So this is like the device, and look, it looks like crap, right? There's all these globs of solder on it and dirt. It's not a perfect device. Okay. But somehow it has a virtually perfect electrical conductance. Okay, and so that raised a puzzle for how could that be. Okay, and so this was a clue. Okay, and so this led geniuses in theoretical physics, people like Bob Laughlin, David Thales, Duncan Haldane. These are people who all went on to win the Nobel Prize for their insights in theoretical physics. It led people like that to think very deeply about what could be going on. Okay? And so the picture that emerged is that what's going on has to do with topology, okay? And in particular, one way of thinking about it is to think about the topology in band theory, okay? And so let me tell you a little bit about what a band structure is, okay? So band theory is the theory of electronic materials, okay? And basically what a band structure is, you can think of it that it's a collection of it's basically a Hamiltonian, which I can think of as a Hermitian matrix, which is parameterized as a function of momentum. Okay, and so this defines a set of eigenvalues and eigenvectors, which are parameterized as a function of momentum, and momentum basically lives on a torus. Okay, so in 2 dimensions, it's the surface of a donut. In 3 dimensions, it's a 3 torus. And but there's something about this which is kind of interesting, which was not really appreciated in the, band theory, again, I said was 80 years old, but what was not really appreciated is, there's something, when you choose the eigenvectors, nobody tells you what the phase of the eigenvectors should be. They're complex vectors, okay, but the eigenvector could have any phase. And that phase can actually change as a function of k. And what that fact means that this band structure defines a vector bundle over the torus of the Brillouin zone. Okay, and so this fact leads to the introduction of topology. Okay, so in fact, band structures, with a gap where I have occupied states and empty states, which are separated by an energy gap, and this is what happens when you have an insulator. You have the occupied states and empty states are separated by an energy gap. That's responsible for the fact that the insulator is electrically inert. Okay, so well, yeah, a single band would be a one-dimensional complex vector bundle. If you have several bands, you might think you should have several one-dimensional complex vector bundles, but I want to allow for the possibility that these bands of occupied states can sort of mix together. Okay, and so what that has the effect of doing is it makes it so that the occupied, if I have n occupied states, that turns into a UN bundle. Okay, so that's actually a very perceptive point. So what happens though, and so this is the realization that again, people like David Thales realized, is that ideas of topology can be applied to these band structures. So in fact, in 2 dimensions, when I just have a Hamiltonian which is a function of 2 parameters, kx and ky, on a 2 torus, then in 2 dimensions the band structures can be classified by their first Chern class. Okay, and basically you can think that my wave functions, the phase can be changed, but that defines I can define a connection in momentum space, and as a physicist I think of this connection as being sort of like a vector potential. Okay, it behaves the same way. So the connection's not gauge invariant, but the curvature or the curl of this vector potential is gauge invariant. And the first Chern class is the integral of that curvature over the entire 2 torus. Okay, and so what we know is that integral is an integer. Okay, and so what Thales showed, one of the things Thales got the Nobel Prize for, was showing that the formula that you get for this is exactly the same formula as what you would get if you calculated the Hall conductance. Okay? So the Hall conductance, this thing that's measured an integer to 1 part in a billion, what you are measuring is you are measuring a topological invariant. Okay, and so that gives you some insight into how it could be that this thing in this crappy sample is so perfectly quantized. Okay, now so band theory, of course, is is a very a broad subject. Now, for a long time, it was thought that this was really the only kind of topological phase that you could have. Okay, and you need. It's important to get the quantum Hall effect. You have to have a magnetic field. Okay, and so you could ask the question, well, what happens if you don't have a magnetic field? Is there anything that you can have? And so this is a question that it took somewhat longer, and it was only in the last 15 years or so that we began to understand. And we began to understand the interplay between symmetries and the topology. And in particular, and so you see, because if you have symmetries, then it can rule out certain topological classes, but it can also introduce new topological classes. Okay, and so in particular, you could ask, what if you don't have a magnetic field? Okay, now if you don't, so you don't put you have this, say, two-dimensional electron gas or some piece of material, you don't put it in a magnet, which is, maybe what is naturally you should think of. And so that has a particular symmetry, which is symmetry under the reversal of time. Okay, magnetic field is created by electrical currents, and so it violates time reversal symmetry. And so you can ask, what if you had time reversal symmetry? Now, if you have time reversal symmetry, then that introduces a constraint on this Hamiltonian, which is a function of k. It basically relates h at plus k to h at minus k. So it adds a constraint, and so you can ask yourself, if I demand that I satisfy this constraint, then what happens to the topological classes? So one thing you immediately see is that the Chern number has to be equal to 0. Okay, because basically, if you do time reversal, the Chern number goes to minus itself, and so if you have time reversal symmetry, it has to be equal to 0. So time reversal symmetry gets rid of the Chern class. Okay, but the thing that had not been appreciated is that actually it gives you something new. Okay, and it turns out that what it gives you, the new thing that it gives you is it gives you a new kind of topological invariant, and this new kind of topological invariant only has two classes. Okay, it's either trivial or it's topological. Okay, and this new kind of Z2 topological invariant can apply to either two-dimensional or three-dimensional insulators. Okay, and in the three-dimensional case, think of it. So a three-dimensional band structure is a structure of a three-dimensional is a theory of a three-dimensional crystal. Okay, and so once we realized that you could have three-dimensional crystals with topological band structures, then it was this race to figure out, well, what actual materials will do this. Okay, and I struggled with this for a while to come up with actual materials. I did lots of Googling of band structures of materials, but we found some, and then it turns out they're all over the place. Okay, there are lots of topological insulators, and what the thing that's special about a topological insulator, it's an insulator on the inside. Okay, so one of the most famous topological insulators is bismuth selenide, and this is just it's a crystal, it's like a rock. Okay, and on the inside it's an insulator. It doesn't conduct electricity, but on its surface it does conduct electricity. Okay, and surrounding the surface is a very special kind of two-dimensional conductor. Okay, you can't get rid of it. If you tried to cut the crystal open, then there'd be a new conducting surface on the interior surface. Okay, you can't get rid of it. It's guaranteed that you have this conducting surface, and this conducting surface has a very specific kind of electronic structure. Okay, and in particular, in its electronic structure, it has what we call a Dirac cone on the surface on the electronic structure. I don't want to get into what that means, but this is a picture of the electronic structure of bismuth selenide, that was done by angle-resolved photoemission spectroscopy. And what you can see is it has a perfect Dirac cone. So this topological insulator really happens it's really come to life in the real world. Okay? Now, how do we think about this Z2 invariant? So there are actually a number of ways of thinking about it, but one of the most interesting ways to think about the Z2 invariant is that it is actually a Chern-Simons invariant. Okay, and so let me try to explain this. Originally my thought was, we're talking about three-dimensional band structures. Okay, and my original thought was, well, there's no Chern number in 3 dimensions. Okay, the Chern number only occurs in even dimensions, and so there can't be any Chern number in 3 dimensions. Okay, but there is a Chern number in 4 dimensions. Okay, and so actually, Shucheng Zhang and Xiaoliang Qi had a very interesting insight, which is, so let's suppose we have time reversal symmetry in this 3-dimensional band structure. Now, what that means is that if I forget about time reversal symmetry, everything's trivial. So I can continuously deform it to a completely trivial insulator, okay, while breaking the time reversal. I have to break time reversal symmetry in order to, if I keep time reversal, I can't continuously deform it into trivial, okay? So what I can do is I have my 3-dimensional, topological, time reversal invariant thing on the equator here. I can, by breaking time reversal, I can continue it to a trivial insulator. But I could also consider the time reverse of that process. Okay, and so that defines for me now a Hamiltonian defined on a 4-dimensional manifold. Okay, and on that 4-dimensional manifold, as we heard in the first talk, that can be characterized by an integer second Chern number, which is the integral of f wedge f over the 4-dimensional space. And this, like the first Chern number, is guaranteed to be an integer. Okay. Now, of course, this integer might depend on exactly what the process I use to smoothly connect my topological insulator to the trivial one. So I could do it in different ways, and I might get different answers for what that integer is. But if I do it, I have to do it the same way on the top and the bottom. And what that means is that the mistake that I will make is only going to be an even integer. Okay, and so whether this integer is even or odd, that is independent of the way that I close it. Okay, and so now once we realize this, if we write this second Chern number, I can use the fact that f wedge f is actually a total derivative. Okay, and what that allows me to do is to write the integral over the top hemisphere as just an integral over the equator of the Chern-Simons 3 form. Okay, and so this Z2 invariant that characterizes this 3-dimensional topological insulator really is the integral over the 3-dimensional Brillouin zone, the 3-dimensional momentum space of the Chern-Simons 3 form. Okay, and this is something which is it's only gauge invariant up to an even integer. So mod 2, it doesn't change. Okay, so that's the topological insulator. Now, so once we realize this, then a very beautiful mathematical structure sort of emerged. And I don't want to go into this in any detail, but one can think about all different kinds of symmetries, and one can think about all different kinds of dimensions, and there's a very beautiful mathematical structure that emerges that has something to do with K-theory, which I don't really understand, but it has, Bott periodicity and all kinds of very nice structures. Okay, and so this was the beginning of a beautiful story. This is all properties, topological structures of band theories. Okay, again, single particle quantum mechanics. Now, single particle quantum mechanics is not the whole story. So the fractional quantum Hall effect is something which was also discovered by the technology of electronic materials. And what it was found is actually that this Hall conductance, which was an integer, can have fractional values. This cannot be understood with single particle quantum mechanics. Okay, and so this was a big puzzle which initiated a revolution in our understanding of many particle phases of matter. And in particular, Laughlin figured out a way of understanding this, which predicted that this quantum Hall state is a very exotic state which can support fractional charge and fractional statistics. And the way we can think about this, the way we understand this now, is that the low energy behavior of this fractional quantum Hall state is characterized by a Chern-Simons effective field theory. And what this Chern-Simons effective field theory does is it essentially captures the essence of what the fractional quantum Hall effect is about. And what the essence of the fractional quantum Hall effect is about is it is about the binding between electric charge and magnetic flux. So electric charge, so an electron basically binds, say, 3 quanta of magnetic flux. And what that does is that locks the electric charge density to the magnetic field, and it locks the electric current density to the electric field. That's the quantization of the Hall conductance. And this allows one to understand the fractional charge of the excitations and their fractional statistics. And so I have 10 seconds left. I want to say just a word about non-abelian topological phases. So I'll say, once we understood that, then, one can think, well, are there generalizations of this, okay? And so there are generalizations, non-abelian topological states, and Mike Freedman explained how those can be used for quantum information to make a quantum computer. One can make either Ising topological order, which he was talking about, which is related to an SU2 level 2 Chern-Simons theory. This is something that arises in the fractional quantum Hall effect and also the topological superconductivity devices that Mike showed you. Mike also briefly mentioned at the end more exotic types of topological order based on Fibonacci topological order. One can have, something based on SU2 level 3 or maybe G2 level 1. The only reason I mentioned this G2 level 1 is because I recently, so I didn't pioneer this, but I recently wrote a paper about this. And so in this paper, 2 of the most prominent references in this paper, one is, of course, to Mike Freedman, who invented the Fibonacci, and the other is to Kumram Vafa, who taught me what I needed to know about G2. And so this is probably the only chance I'll ever have to have them both in the same audience. So I just wanted to mention that. Okay, so let me just, so I'm out of time. Let me just close. There are many, many applications of these topological ideas. Okay, and there's a whole field of physics now, which is sort of resonating between theoretical physics, computational physics, and experiment. And there's a frontier, which is can we make these strongly interacting topological phases? And thank you very much.